Hi, my name is Colin Thurston, and I will be discussing the effects of oral protein loading on renal sodium and potassium handling during prolonged mild hypohydration. So within the last decade, we have been subject to more frequent and more extreme heat waves. Just a few years ago, the Pacific Northwest suffered 4 consecutive days of over 100 degrees Fahrenheit during the heat dome. Occupational heat exposure has been previously linked to the development of conditions such as kidney disease, which can be worsened by dehydration. Dehydration has already been shown to negatively affect many other diseases like obesity, diabetes, and cardiovascular disease. This is problematic because 70% of people in the US consistently do not consume enough water throughout the day, and 40 to 70% of construction workers start off their day already dehydrated, which dehydration we will refer to in the present study as hypohydration. And so as a way to alleviate this, people often use protein drinks to increase their water intake while supplementing their daily calorie consumption. I can attest that in the 6 years I worked in construction, the majority of shifts started very early in the morning. And with those extra few minutes of sleep being crucial, it can be common for this population to skip a full breakfast and replace it with something quick like a protein shake. Now, we don't know if drinking protein like this, specifically when hypohydrated, alters the urine concentrating ability of the kidneys. Typically, large oral protein loads enhance the urine concentrating ability, but whether this effect occurs when hypohydrated, as is frequently seen at construction sites, has not been studied. And so in the present study, we investigated the effects of protein ingestion on the kidney's ability to concentrate the urine following prolonged mild hypohydration. In a block-randomized crossover design, 22 young healthy adults completed 2 experimental trials, one when hypohydrated and the other euhydrated. Participants completed a 24-hour protocol prior to completing baseline measurements. For the euhydrated condition, this 24-hour protocol consisted of normal fluid and food intake, but for the hypohydrated condition, subjects were asked to limit any high water containing foods and restrict any fluid intake as to induce a state of low body water. After the baseline measurements, subjects were then given a protein shake containing 1 gram of protein and 10 milliliters of water per 1 kilogram of body mass. Additional measurements were then taken at 75 minutes and 150 minutes after the ingestion of the protein beverage. The fractional excretion of both sodium and potassium were analyzed using flame photometry, the gold standard of measuring electrolyte concentration. Data was then analyzed using a 2-way repeated measures ANOVA and presented as means with 95% confidence intervals along with their individual values. And so before presenting these results, I want to briefly orient you to the figures, starting in the top left corner of the results section. This graph represents the effects of hydration conditions, listed on the x-axis, on the change in body mass, listed on the y-axis as a percentage. The individual data for each participant can be seen as the line between the two conditions. The open squares represent the female participants, and the open circles represent the male participants. The combined averages, as well as the standard deviations, for each hydration condition are also shown in the figure. For all the other graphs, the x-axis lists the time of analysis, pre-protein, 75 minutes and 150 minutes protein, and the y-axis being the desired variable being measured, such as serum sodium or fractional excretion of potassium. The average participant data is also shown for each hydration condition, with the closed circles indicating the hypohydrated condition and the open circles indicating the euhydrated condition. The individual participant data is also shown in the background of each graph, with the solid gray line showing the hypohydrated participants and the dashed gray line showing the euhydrated participants. With that being said, the results of our body mass data showed that there was a significant decrease in the average body mass during the hypohydrated condition, but no change during the euhydrated condition. This confirms that our 24-hour protocol of restricting food and fluid deprivation was effective in reducing the amount of water in their body. With fractional excretion of sodium, we can see a significant increase following protein ingestion at the 75 and 150 minute time point for both the hypohydrated and euhydrated conditions. When comparing the hydration status, we can see that hypohydrated subjects started significantly lower in their fractional excretion, but this difference was not maintained during the 75 minutes and 150 minutes after the protein ingestion. With fractional excretion of potassium, we observed a significant increase following protein ingestion, 75 minutes and 150 minutes after protein ingestion, for both the hypohydrated and euhydrated conditions. Looking into each time point, we can see that at all time points, the fractional excretion of potassium was significantly lower in the hypohydrated conditions. And so in conclusion, these findings indicate that the fractional excretion of potassium during hypohydration is initially lower compared to euhydration, but is not different between conditions at the end of oral protein loading. In contrast, the fractional excretion of potassium remained lower throughout the experimental protocol in hypohydrated versus euhydrated. These data suggest that a large protein bolus during prolonged mild hypohydration does not alter the kidney's ability to regulate blood sodium. Our findings support previous work demonstrating that protein may be beneficial as part of a rehydration solution, including that the large protein bolus used in the present study did not negatively impact urine concentrating ability. Future studies can explore the addition of other ingredients such as glucose, sodium, or caffeine into high-protein beverages that may alter these responses, given the prevalence of individuals consuming these prior to occupational heat stress. Thank you.